Scientists have long been fascinated by black holes, a concept that illustrates Einstein's theory of general relativity and has garnered special attention. Black holes are often described as omnipotent destroyers that capture and crush everything around them. We know that nothing can escape from a black hole. But what happens to the things that fall into it? What is the reality inside a black hole? It can be said that black holes are the strangest things that have ever existed. The theory of their existence appeared nearly a century ago. We have had convincing evidence for 30 years of observation. However, astronomers still do not fully understand them. A black hole, with a mass 4 to 5 times that of the Sun, and only a few kilometers in diameter, causes space to bend so strongly that the degree of gravitational force changes significantly, even over distances as short as a human body. If you fall into the vicinity of a black hole, your feet will accelerate faster than your head, stretching your body in accordance with gravitational forces like a medieval torture rack. This phenomenon is the extreme version of tidal forces and ultimately disintegrates you in a process known as spaghettification. As the atoms that make up your body cross the event horizon, an invisible boundary that once matter crosses it cannot escape the black hole. You become part of the mystery that has not yet been answered within the black hole. Despite being called a black hole, the first vague perceptions of the existence of black holes appeared in the 18th century, when geologist John Litcher wrote a letter to the Royal Society of London, suggesting that a star 500 times larger than the Sun would generate a gravitational force so strong that not even light could escape its grasp. Michel's inspiration was passed on from natural philosophers of the time, who had succeeded in measuring the finite and constant velocity of light. James Bradley, the third Astronomer Royal, was the first to calculate the speed of light, and these results are still accepted today. In 1728, while working at the Greenwich Observatory in London, he discovered an odd shift of the stars, initially thinking he had found parallax. He soon realized all the stars he measured had the same shift in origin. So the effect we call the parallax, which varies with the distance of the star from the Earth. He attributed the shift to the finite speed of light, akin to tilting an umbrella forward in the rain, because your movement makes the rain seem to fall at an angle. This angle helped Bradley calculate the speed of light based on the speed of the Earth, around 300.0 cos. Michel used Bradley's calculation in his theory of universal gravitation to estimate the size at which an object achieves escape velocity at the speed of light, reaching a result of about 500 times the mass of the Sun. This concept sparked a heated debate for many years as astronomers grappled with the possibility of dark stars. Eventually, natural scientists concluded that Newton's laws had ruled out light from the influence of gravity, and therefore light always escaped any celestial body, no matter how strong its gravitational force. The issue remained unresolved for 2 centuries until Einstein published the theory of general relativity in 1915, showing that gravity indeed affects light, just 2 months after Einstein's publication. German mathematician Carl Scheel discovered that Einstein's equations allowed for celestial bodies so dense that they formed gravitational traps. The size of each trap, also known as the Schwarz radius, depends on the mass within. For example, a black hole the weight of Earth would have the size of a small coin, while a black hole billions of times the weight of the Sun would have a similar radius encompassing our solar system. Any object, including light, that crosses the still horizontal radius, also known as the event horizon, will never escape. Astronomers had to accept that black holes could exist, but paradoxically, how can you observe something that emits no light or any kind of radiation? It wasn't until the early 1970s that the answer emerged when the first X-ray telescope was launched into space, discovering an extremely bright X-ray source in the constellation Cygnus, about 8.0 light-years away. After much analysis, scientists concluded that the X-ray source was a superhot gas cloud being pulled into a black hole called Cygnus X1, as the gas stream accelerated in the extreme gravitational field outside the event horizon. It heated to millions of degrees and began to emit X-rays. Since then, many observations have focused on a black hole devouring. For example, by tearing apart a companion star, the supergiant blue star had 226,868 is more than 30 times the mass of the Sun and 400.0 times brighter. The black hole beside it only contains 5 to 10 times the mass of the Sun, but its gravitational force is so strong that it pulls the giant blue star into an X shape. And now, even more really, it absorbs its gas. The gas from its giant blue sperm moves into a spiraling orbit around the black hole, forming what astronomers call an accretion disk. The swirling region of the disk, some gas is flung out into jets shooting away from the black hole. However, most of the gas eventually falls into the black hole, vanishing like water swirling down a drain, never to be seen again. Black holes like Cygnus X1 are called stellar black holes. They have a mass several times that of the Sun and form when very large stars explode as supernovas. A supernova is triggered when the ion core of a star collapses into a neutron star or the outer layers of the star collapse in, igniting the supernova explosion. The neutron star at the core is compressed and absorbs some of the outer material, increasing its mass. The core's gravitational pull can become so strong that it collapses into a black hole. Besides the stellar black holes mentioned above, there are other types of black holes that are larger and have different formation mechanisms. Intermediate mass black holes are similar to stellar black holes, orbiting in the surface of their clusters, and weigh a few hundred to a few thousand the mass of the Sun. Astronomers are uncertain how they formed. They might be a result of several stellar mass black holes merging. The third type is supermassive black holes, which contain mass millions to billions of times that of the Sun. It is believed that a supermassive black hole resides at the center of every galaxy. They don't occupy more space than an average solar system. 90% of galaxies, like ours, have a dormant supermassive black hole at their center. In the remaining 10%, it actively feeds on nearby celestial bodies, creating a spectacular machine observable from billions of light years away. An active galaxy releases more energy every second than 1,000 trillion suns, all from matter heated before falling into the supermassive black hole at its center. The active galaxies are hundreds of times brighter than the rest of the galaxy, hiding the active core for a long time, when first encountered in the 1950s. Astronomers saw the cores of active galaxies as stars, and thought they were peculiar stars in our galaxy. They were referred to as quasars, a name that persists today. The nature of these stars was revealed in 1962, when astronomers discovered their unimaginable distance, meaning they couldn't be stars, but were immensely powerful galaxies. Black holes continue to challenge our understanding of the most basic laws of physics. Even if a black hole isn't completely dark and isn't a hole, but a fuzzball of quantum strings, there is consensus that no one would want to fall into one.